Hello everyone. By now you should be familiar with the term principle of moments. Now, principle of moments refers to the sum of clockwise moment about a pivot is equal to the sum of anti-clockwise moment about the same pivot. Now, it's very common for students to leave out the pivot for reasons that can't be explained. And I'm going to use this example to illustrate to you how important the pivot is and how it actually affects the equation that you're going to form to solve your everyday problems. Now over here we have the figure that shows an electrically operated railway crossing barrier. Now it's very similar to the multi-story car park barrier that you have in Singapore. The barrier is pivoted at P, and in order to make it easier to raise the arm of the barrier, the weight of the arm is balanced by the counterweight M. Balance. Now this should give you a clue that most likely we need to use principle of moments to solve this problem. Now the weight of the arm is 250 newtons and its center of mass is 2.4 meters from P. So you have 250 newtons and 2.4 meters from P. And you have the pivot P. And the center of mass of M is 0.4 meters from P. So you have 0.4 meters and this is the weight of the mass. You're supposed to calculate the value W, which just balances the weight of the arm. Just balance the weight of the arm. Now, how do you go about solving this problem? So I'm going to solve this problem with two solutions, and I'll try to the best of my ability to convince you that, well, in sometimes when the position of the pivot is not given, you can choose any point to be the pivot. And that's the wonders about problems like this. First, you have the point pivot, and it's represented by a triangle, which I've drawn there. Now, with this point fixed, W will turn about this pivot in this direction. Okay, turn about the pivot, right? Now, note that many students, when they see this kind of problems, they don't do this. They go and turn into the pivot. Right? No, that is not the point. All right. The point is when you have an anchor there, how will W rotate? W will actually rotate around the pivot. Right? You see the way I draw the circle? W will rotate around the pivot in this direction. And that's what's contributing to the anti-clockwise moment. And 250 newtons will rotate about the pivot, and this will contribute to the clockwise moment. So how are we going to solve this? So for first method, we're going to take moments about P. So we're going to take moments about P, which means to say what I'm actually calculating is clockwise moment, anti-clockwise moment about P equals clockwise moment about P. So if I take anti-clockwise moment about P, I have W times 0.4 meters. Clockwise moment about P, I have 250 Newton times 2.4 meters. And W will give me 1500 newtons. There you have it, 1500 newtons. Now, that's using principle of moments, and I choose point P to be the pivot. What if I decide not to choose point P as a pivot? It can be solved. So that's the wonders about this kind of problem solving. Yes, you will learn the formula moment equals force times distance, but the fundamental here is you have the understanding that the in the principal moments, the sum of clockwise moment equals the sum of anti-clockwise moment. This is understanding the principle behind it. Which means to say, the definition itself didn't state where the pivot must be. So I'm going to show you another way to solve this problem, and I'll choose the pivot. This time round, let's say I choose the pivot at the 250 Newton. I put my pivot here. So I have an unknown W and I have an unknown P. What's my force at the pivot P? So actually the force at pivot P, you can use Newton's third law to solve this. I have an action W, I have another action 250 Newtons. So I have an action W plus 250 Newtons. So by Newton's third law, for every action, there's an equal but opposite reaction. So my reaction is W plus 250 Newtons. So P is no longer an unknown. I actually use Newton's third law to find out what P is, what the force at P is. And as we delve into it further, with a pivot at 250 Newtons, W will cause the structure to turn in this manner, and it's a anti-clockwise moment. W will cause the structure to turn in a clockwise moment. And let's call this pivot point X. So if I were to taking moment about X, anti-clockwise moment about X equals clockwise moment about X. So anti-clockwise moment about X. So you have the length that stretches this whole stretch. And anti-clockwise moment about X, you have W times 2.8. Right, 2.8 will come from 2.4 plus 0.4. Clockwise moment, you have W plus 250 Newton times 2.4. So if I want to rearrange it, I have 2.8 W equals 2.4 W plus 600. And when I bring it over, I have 0.4 W equals 600. W equals 1500 Newton. And I have the same weight back. You see, so in my second approach, instead of worrying about the unknown, we use a basic Newton's third law to find the unknown, and that's W plus 250. So here, what I've shown you here is that when solving problems using principle of moments, well, most of the time the pivot is quite obvious in your papers, but sometimes when it's not obvious, be brave enough to pick a pivot. Right, when you pick a pivot, make sure the perpendicular distance can be measured. Okay, if it cannot be measured, don't forget about that point. All right. So most importantly, pick a pivot, and then identify a clockwise and an anti-clockwise, and then solve it. Okay, so that's about it for this section.